let's look at an application of the Maclaurin series for square root of 1 plus x. So we're going to rewrite that as 1 plus x to the 1/2. Maclaurin series means center is at x equals 0. Our Taylor coefficient formula is going to be a sub k equals kth derivative of f evaluated 0 divided by k factorial. Once I get all those coefficients, we're going to load them into a power series as so. So a sub k goes with x to the k. So let's start churning out a few things. We'll note some relations, and then we'll see how we can use this to get something interesting. All right, so if I start calculating these, so what do we have? So first, we'll do f of 0 is equal to 1. So a0, that's going to be, our 0th derivative is just the function, and then 0 factorial is just 1. So a0 is equal to 1. Take my first derivative, we bring the half down, take 1 off the exponent, derivative of the inside is just going to be 1. So f prime at 0 is going to be equal to a half, and then we take that, divide by 1 factorial, which is 1. So a sub 1 is going to be 1/2. Go to the second derivative. So what are we going to do? We're going to bring that minus a half down. Then we're going to take 1 off of that, giving me a minus 3/2, and then derivative of the inside's 1. So evaluated 0, that's going to give me minus 1/2 times a half. And then we're going to divide that by 2 factorial, which is 2. So a2 is going to be minus 1/8, but we'll leave it like that just so it's suggestive. Going one more, I'm going to bring that minus 3/2 down. We're going to take 1 off the exponent, and then derivative of the inside still 1. We put our 0 in, so we get minus 3/2 times minus a half times a half. Then we're going to divide by 3 factorial. So for a sub 3, we get minus, okay, the 3's will cancel, so it's going to be minus 1/16. Okay, why did I do so many? If you look carefully, you'll see a pattern in here. If I take the k plus first derivative, what am I going to do? I'm going to bring the exponent down. That exponent, if I'm looking at k plus 1, the exponent's going to be 2k minus 1 over 2. It's also going to have a minus sign on it. So this is going to be the exponent we bring down. And then you'll notice, what do we do when we subtract 1 off of the exponent? That's just taking the derivative that we had before and then dividing by 1 plus x. Okay, and the derivative, writing it like this, is going to pick up all the extra terms that we're collecting as we move down the derivative. So we have one term coming down from the exponent, and then we'll have a bunch of terms that are just from the old exponents. Okay, so I get this formula here. I'm going to put 0 in, and then you're going to notice your fk is 0, stays as it is. I'm going to have 2k minus 1 over minus 2. Then we have fk plus 1 over 0. Now what I want to do is divide by k plus 1 factorial. So that way I get my a sub k plus 1 on this side. On this side, we don't need a k plus 1 factorial. I just need a k factorial. That's going to divide into my fk evaluated 0, which is going to give me a sub k, and what will be left over is going to be minus 2k minus 1 over 2k plus 2. So this relation I'm going to use by putting the a sub k in the denominator on the other side. All right, now, this seems like a lot of work. What this is going to get me is the interval of convergence and a rule for churning out more of these coefficients without having to take derivatives. Okay, so if you notice, I put the a sub k to this side. Then what do we have here? We're looking at limit n going to infinity, a sub n plus 1, x n plus 1 over a sub n, x to the n. This is just my ratio test, which I'm going to use to get my interval of convergence. Well, when we collapse this part here is just going to go to absolute value of x. And then you notice here what's going to happen. Minus sign goes away, and I'm left with 2n minus 1 over 2n plus 2. I take the limit as n goes to infinity, and then I'm just going to be left with absolute value of x. And then the ratio test will say this converges whenever what comes out is strictly less than 1. And then that's going to be the interval minus 1 to 1. All right, not the most important part of this, but I just wanted to go through that because this trick is really useful to have, and you should see it at least once in one of the series that we do. All right, so summarizing, our f of x is going to be equal to square root of 1 plus x, and then this is what I get out when I write out the first 5 terms. So we already saw the first 4, And then this one I can get just by applying our formula here. So to get the fourth term, I'm going to put a 3 in there. That's going to give me 2 times 3 minus 1 is 5. And then a 3 in the bottom is going to give me 8. 8 times 16 is 128. Okay, let's do something useful. I'm going to take the derivative of this. So we do the derivative term by term. On this side, we're going to get that 1/2 comes down, 1 plus x, take 1 off the exponent. And then we just go term by term. I'm going to get a half. This is going to go to a quarter. The 3 comes down, give me a 3/16 x squared. The 4 comes down. 4 goes into 128 32 times, and so on. So that's going to give me power series for 1 over 1 plus x to the 1/2. Okay, 2 steps away from something cool. What I want to do now is, if I think of this as 1 over 1 plus something in the box, I'm going to replace what's in the box with a minus x squared. So wherever I saw an x before, I put a minus x squared, which changes this series into 1 plus a half x squared plus 3/8 x to the 4th plus 5/16 x to the 6th. Now on this side, this should look familiar. This is the derivative of inverse sine. So what I'm going to do now is I'm going to integrate both sides, and then that's going to give me the formula for inverse sine. So I take any derivative here, I get inverse sine. Any derivative here, I'm going to get c plus x plus 1/6 x cubed plus, okay, that's going to turn to a 5, so I'll get 3/40 x to the 5th. Then add 1 there, it's going to turn to a 7, gives me 5 over 112 x to the 7, and so on. Okay, we want to get rid of the c, so I'm going to put 0 in for both sides. Sine of 0 is 0, so we translate that as by pushing the sign to the other side. Sine inverse of 0 is 0, that means c is 0. So now, add the power series formula for sine inverse. Now, having that, that's fine and all. Let's actually put a number in there and see how close we get. So if I put 1/2 into here, it's going to give me a half. Okay, half cubed is 1/8, so I'll get 1/48. Then it's going to be 1/32 times 3/40, gives me that. And then we'll do one more, so it's going to be 1/28 times 5 over 112, which gives us that. Push it through a calculator, what are you going to get? You're going to get 0.5235, and you'll notice that's extremely close to pi over 6, which is what we would get for inverse sine of 1/2.